Welcome to a new video, everyone. We're going to learn in this video about humidity. And for that, we have a lot of new terms. I have all the definitions of these terms in here. You can take a screenshot of it if you want. You can look at it. We're going to go over them throughout this video. And this video, mostly, I'm going to use it. I have also this interesting fact you can read on your own if you pause the video. But throughout this video, I'm mostly going to use I'm gonna handwrite the solutions for every single part of it. So to get familiar with the humidity, we have the following statement. For the official Salt Lake City weather station at the airport and for the month of August, the following were found. We're given the monthly average air temperature, 77.9 Fahrenheit degrees Fahrenheit, which is equals to 25.5 degrees Celsius, and it is equals to 298.5 degrees Kelvin. And we're having all these different units of temperature because we're gonna need them all to solve the following problems. Then part B, that also gives us the monthly average relative humidity, which is 31%. We need to find, it says, using the above data and assuming standard sea level atmospheric pressure in millibars, determine the mean monthly. We need to find part A, saturation vapor pressure, and all of these values. We're gonna go each by one by one. Again, all the definitions of what each term means is here. You can pause it if you want to be reminded. And we're going to use table B.9 and table B.7 to solve for some of these terms. So starting with part A, we have that we're asked for the saturation vapor pressure. And for that, we're going to use table B9. And that's because we need that the table helps us to find that in here, saturation vapor pressure. So the way you read the table is very simple. Uh, for a given temperature in Celsius and for a given saturation vapor pressure, either in millibars or in inches of mercury, we have a wet bulb depression in degrees. It could be any of these values, right? So on the first problem, part A, we ask for the saturation vapor pressure, which we can use these two columns. So we know that we have 25.5 degrees Celsius, so it will be between these two values, and it will, for that corresponds a value here in millibars between these two values. So let's go ahead and use our forecast formula. So we have 24, 26, 29.83, 33.61, and these two values are the ones here, 29.83, 33.61, and we are interested on 25.5, right? So we're gonna use our forecast linear in our case, and we're interested in this value, 25.5, and our data in Y will be this, and our data in X will be this. So our answer will be 32.6665 or 0.67. And that's the answer for part 5. Now let's delete all of this because we're gonna need it, and we're gonna need the space. Now part B, the actual vapor pressure, we're asked for that in millibars. So to solve that, we're gonna use this equation right up here. These are some of the useful equations that we're gonna use to solve for these terms. And part B, we're gonna use this one here, which would be something like F equals E over E sub S. We're asked for the actual vapor pressure, which is E. That will be F times sub S. So we are given the F, which is the relative humidity, we're giving is 31%. So it will be 0.31 times 32.67 millibars that we solved in part A. And this should be 10.13 millibars. And that's the answer for part B, 10.13 millibars. Now for part C, we're asked for the water vapor density, or also called absolute density, sorry, absolute humidity. And for that, we're gonna need this equation right here, and we'll need the temperature and degrees Kelvin. So that would be water vapor density equals to E RV, temperature of the air. RV, we have the value here, is the gas constant for water vapor, and is 462 joules per kilogram times degrees Kelvin. So the way we're gonna solve this is, for this equation, E we have solved, that is 10.13 millibars. Now this millibars, we need to convert it to newtons per meter square, and we have here in this conversions and constants table that 1 millibar equals to 100 newtons per meter square. So we're gonna do 100 newtons per meter square equals 1 millibar. So millibars cancel, and we have as an answer 10, 13 newtons per meter square. And our RV, we know that we're giving is 462 joules per kilogram times degrees Kelvin, and that's equal to 462 newtons times meter, because that's a joule, over kilogram degrees Kelvin. And our temperature, we know now, we have converted, it's gonna be 298.5 degrees Kelvin. With these values, now we can solve for the water vapor density. This is going to be equal to 10, 13 newtons per meter square over 462 newtons meter over kilograms degree Kelvin times 298.5 degrees Kelvin. Degrees Kelvin cancel, newtons cancel, and we're gonna have 0.00735 kilograms per cubic meter. And we want to convert this into grams. So in one, there are 10 times 10 to the third grams, or 1,000 grams in 1 kilogram. So kilograms cancel, and our final answer should be 7.35 grams per cubic meter. And this will be the answer for part C. Now for part D, we're being asked for the dry air density in grams per cubic meters. So for that equation, we're gonna use this one in here, and that would be that the atmospheric pressure equals to the air density times air, that is the gas constant for dry air, and times the temperature of the air. Now for this, the atmospheric pressure, we're gonna use 10.13, sorry, that's not point, it's 1013.2 millibars. Now we need to convert these millibars into newtons per square meter. So millibars cancel, and we're gonna get 10, 13, 20, newtons per square meter. That's the atmospheric pressure. Now, the gas constant for dry air is equal to 287 joules per kilogram degrees Kelvin. And as we did before, 1 Newton times meter equals to 1 joule. So joules cancel, and we have 287 newtons meter kilogram degrees Kelvin. And this is so we have newtons in all our terms so that we can cancel it, right? And then we know that the temperature of the air in Kelvin is 298.5 degrees Kelvin. Now, to solve for the dry air density, which is here, we can use the first equation, that equation, and so it will be air density equals 1320 newtons per meter square all over 287 newton meters over kilograms degrees Kelvin times 298.5 degrees Kelvin. We cancel degrees Kelvin and we cancel the newtons, and we are left with the air density equal to 1.18 kilograms per cubic meter. And converting that into grams, there are 1,000 grams in 1 kilogram. Kilograms cancel, that's going to be 1,182.7 grams per cubic meter. And this is the answer for part D. Now for part E, we're asked for the mixing ratio. And the mixing ratio is denominated as R, and the equation will be this equation here that I'm highlighting. Is R equals to density of the vapor, water vapor, over density of the dry air. And we have solved already that this is 7.35 grams per cubic meter, and the density of the air equals 1182.7 grams per cubic meter. So solving for that, for these two values, we have 7.35 over 1000, and they both have the same units, so the units cancel, and that's going to be equal to 0.006, about 62.1, which is about 6.21. And so that should be the answer. And then for the next part, we need to solve for the specific humidity. And the equation for that is the next one here. And that will be QH equals water vapor pressure over water vapor pressure plus the air density. Sorry, this is not pressure, these are densities, water vapor density. So, and we have that this value, we solve for that, 7.35 grams per cubic meter, and the air is 1182.7. This is 1 grams per cubic meter. Solving for that, we're gonna get about 6.176 grams per kilogram when we do the respective conversions. And this should be the answer for that part. Now the wet bulb depression, for that we're going to use table B.7 that I have down here. So we are given that the temperature is 25.5 degrees Celsius. So that will be right about between these two values. And we know that the relative humidity is 31%. So this table is to find actually the relative humidity, which will be any of these terms here that I'm trying to highlight here. Any of these terms will be the relative humidity based on the wet bulb depression and the air temperature in degrees Celsius. However, we are looking for the wet bulb depression because we have the temperature in degrees Celsius and we have the relative humidity. So we need actually to find a value up here based on the value that we have. And we're looking for 25.5 degrees Celsius and we have a 31% relative humidity. So eyeballing would be something we can look for when we get closer to 31, and it's right about here. So, but this is not 24, the value. This 31 belongs to 24 degrees Celsius. We are interested in 25.5. So we could do linear regression, or we could also just like eyeball and have a rough idea of like what would be. So this 31 um, belongs to 10, uh, to a value of 10 for the wet bulb depression. So since we are looking for a higher degrees of degrees Celsius, I would say it's about 10.5. So the answer for that part, it would be 10.5 degrees Celsius of wet bulb depression. So that would be the answer for that part. So that would be the wet bulb depression will be 10.5 degrees Celsius. That's that's the answer for that part. Now the wet bulb temperature, that will be the wet bulb temperature will be like the temperature average, that in our case is 25.5, minus the wet bulb depression. So this is 25.5 degrees Celsius minus 10.5, because that's what we just solved. 10, oh, 10.5 degrees Celsius. And this will be about 15 degrees Celsius. And that's the answer for the wet bulb temperature. And based on that, we can also find the dew point temperature, which will be the last part, I. And so for that, we'll need table B9 again. And table B9 will help us because with a temperature of 25.5, we'll actually have to use some linear regression here because it's a little harder to do. And okay, so 25.5 will be between 24 and 26. And then we have a wet bulb depression of 10.5, but there is no 10.5, will be in between these two values. So let's find first what would be the value corresponding, what value here would be corresponding to 25.5. So we have 26, and then we have, no, this would be, we have 24, 26, and for 24 on the value of 10 will be 6, and for the value of 10 the 26 would be 9. So this is 6, this is 9. And I don't know what this is. Let me change this. 9. So we're interested in 25.5. So we use here our linear regression, and we're interested in 25.5. This will be our y data. This is our x data. So for for 25.5 degrees Celsius, we have, and a wet bulb depression of 10 corresponds 8.25 dew point, variation of dew point. Now let's do the same. Let's have the same approach, 24, 26, and we're interested in 25.5 for the value of 11. So in 11, 24 will be 3 and 6. So it will be 3, 6, and we'll do the same. Forecast that linear, interested in 25.5. and this will be the value for 26. Now, if we move this down, we can do the same approach, but inverse. Now we need to know the 10.5 value, right? So, and we have the values for 11. So the value for 10 is this one here, right? 8.25. And the value for 11 will be 5.25. So we're interested in 10.5, and this will be equal to the forecast of what 10.5 will be. This is our y data, and this is our x data. So our result will be 6.75, and this will be the dew point temperature, 6.75, which will be about 7 degrees Celsius, right? Because this is degrees Celsius, this value. And that's the last part, that's I. So this is how you solve using these equations, using the tables b.9 and b.7. This is how you solve for each of one of these terms. Now, if you don't completely understand what each term means, I have some definitions here, and for each one of these terms as well. So I hope you find this helpful. In the next video, we're gonna do a review of what we have covered so far. I think that will be a short but very useful video for you to watch, and make sure if you are understanding these new concepts. And from then on, we're gonna be working with hydrographs and keep working with runoffs. And that's it for now. Good luck working out these problems.